Hello students, welcome to the fourth lecture of first unit solutions. This lecture is in continuation to the third lecture in which you learned about solubility, solubility of solute in solvent. In third lecture, we discussed solubility of solid in liquid and solubility of liquid in liquid. You learned there were various factors which affected their solubilities, like nature of solute, nature of solvent, then temperature, and about pressure. You have learned that pressure does not affect solubilities of solid and liquid solutes because solid and liquid is practically incompressible. So pressure has no role to play in their solubilities. In today's lecture, we are going to discuss solubility of gas in a liquid where pressure has great role to play. Of course, temperature also, but here pressure will also affect the solubility. So now let us study solubility of a gas solute in a liquid solvent. From our general observation, we observe that when some gas is dissolved in liquid, for example, we drink cold drinks. In cold drinks, the cold drink bottles are tightly closed. They are closed under pressure. Why? Of course, to increase solubility of CO2 gas in that liquid, in that water or that sweet uh, drink, because the solubility of gases increase with increase of pressure. What? Solubility of gas increase with increase in pressure. Okay, now question is why? Why solubility of gas increase with increase in pressure? See in these diagrams. In this diagram, you see this is pressure. This weight is there. It is a piston, you can say. So this lower part is liquid. Upper part is gas. So this is liquid, this is gas, and this is some kind of pressure, you see. And in this system, there exists equilibrium. Equilibrium is always there. At all temperatures and conditions, pressures, some liquid molecules must be evaporating, going into gaseous form. Some gas molecules must be going into liquid form. And an equilibrium will be existing here. Now what happens? If we increase this pressure, the piston will go down. What will happen? If this gas molecules remain here, gas molecules will come close to each other. Number of collisions among gas molecules will increase and it will increase the pressure of gas. Gas molecules will come close. Number of collisions among themselves and number of collisions on walls of this container will increase. You know, pressure of a gas is due to collisions made by gas molecules on the walls of container. So pressure of gas will increase. Now, according to Le Chatelier's principle, you always remember this principle. This principle is going to help many things, many situations. Le Chatelier's principle. So this principle states that whenever stress is applied on a system in equilibrium, the equilibrium shifts in such a direction so as to undo the effect of stress. Now, what will happen? Liquid molecules are going into gaseous state, gas molecules going into liquid state. Both are opposite processes and are in equilibrium. So pressure remains constant. When we have increased the pressure, according to Le Chatelier's principle, the equilibrium will tend to decrease pressure. And how is that possible? That is possible only if gas molecules go into solution. If gas molecules go into liquid to form a solution. Okay, so that means solubility. When liquid molecules are going into solvent, that means their dissolving solubility is increasing. So solute is gas, solvent is liquid, and solution is being formed. And when gas comes out, solution is disturbed. And here, pressure will become low. Pressure is decreasing. Here, pressure is increasing. So, there is equilibrium. If we increase the pressure, the situation will be, if we increase the pressure, the equilibrium will shift in forward direction. One thing, I have written it wrongly here. Pressure will be high here and low here. Try to understand once again. When solvent, liquid, and solute, gas, are separate, pressure is due to gas. Liquid has no pressure. Okay. So here pressure is high. Okay. And when gas has entered into liquid, it has become solution, pressure has decreased. So if pressure is increased, the equilibrium system will tend to go towards that side which involves decrease in pressure. That means in this direction, in forward direction. So solubility will increase. And if we decrease the pressure, if we pull this piston out, what will happen? Pressure will be decreased. Now, equilibrium system will have a tendency to increase its pressure. And for that purpose, the gas solute will come out of the solution. You must have seen when we open a cold drink bottle, gas comes out, fizz comes out. And that comes out because pressure is decreased and equilibrium shifts in towards backward direction. Okay, now you got it. So in this way, Le Chatelier's principle explains that solubility of a gas is affected by pressure. Solubility increases when pressure above gas, which is in contact with the liquid you see here, this is liquid, this is gas. When both are in contact, pressure is above. So when pressure increases, solubility increases. Now, this phenomenon was observed carefully by careful experiments. A scientist, Henry, derived a law, which is called Henry's law. This is in our syllabus. We will derive its formula and also solve some numerical problems based upon it. First of all, what is the statement of Henry's law? Very simple. Henry's law states that at constant temperature, this is important, at constant temperature, the solubility of a gas in a liquid is directly proportional to the pressure of gas. Okay, at constant temperature, temperature remaining constant, solubility directly proportional pressure. Means the more is pressure, the more will be, the higher will be solubility. That's it. Okay. If we use the mole fraction of gas in the solution as a measure of solubility. Now, what is the measure of solubility? When a solution is formed, now solution has two components. One component is water, other component is gas. And you know, in this binary solution, there will be mole fraction of water and mole fraction of gas. The mole fraction of gas, if is higher, that means its solubility is more. If lesser, solubility is less. Means mole fraction of gas in this solution can be taken as a measure of solubility. Okay, so if we use the mole fraction of a gas in solution as a measure of solubility, then it can be said that mole fraction of gas in solution is proportional to mole fraction of gas in solution is proportional to the partial pressure of gas over the solution. Okay, so see again, mole fraction of gas in this solution is proportional to pressure of gas over the solution. Okay, the more is this partial pressure of gas, the higher will be its mole fraction in solution. That means the higher will be its solubility. So this is another form of this statement. This statement. This statement is just written in this form. Both say same thing. You must keep these two in mind. The most commonly used form of Henry's law states that the partial pressure of the gas in vapor phase is proportional to the mole fraction the gas in the solution and is expressed as P is equal to pH into X. What is P here? P here is pressure of gas, partial pressure of gas, you can say. KH is Henry's law constant, and X, you know, mole fraction, which is a method of expressing concentration. Okay, so KH is Henry's law constant. I think you got it. That solubility of a gas in liquid increases with increase in pressure. It is explained by Le Chatelier's principle. And Henry's law states that mole fraction of gas in solution is proportional to partial pressure of the gas over the solution. Now let us take a graphical form. In this graph, you see partial pressure of HCl is plotted against mole fraction of HCl. And when partial pressure is increasing, mole fraction of HCl is also increasing. You know, HCl is highly soluble in water. Many gases are more soluble than others. Oxygen is slightly soluble in water. Percentage of oxygen is about 0.03% something in water. And that dissolved oxygen is available to aquatic plants and animals for living. But HCl is highly soluble. Its solubility is about 90%. Why? Nature of solute, nature of solvent. HCl is a polar substance, you know, and water is also a polar substance. Like dissolves like. Those two factors will remain. Here also, in solubility of gas in liquid, also nature of solute, nature of solvent, their chemical nature is going to affect. And pressure also is playing its role. Next, here in this table, KH values of some gases are given at constant temperatures. You can see if temperature is 293, KH of helium is 144.97, H2 is 69.16. Can you tell me from He and H2, which will be more soluble? The gas having higher value of KH or lesser value of KH? This is the relation. This is the relation. If KH is more, the partial pressure will be more, or if we manipulate it like this, see, from here you can draw the inference. If we write this relation like this, P upon KH is equal to X. Or if I write like this, X is equal to 1 by KH into P. What is P here? Partial pressure. X, mole fraction. 1 by KH, reciprocal of Henry's law constant. Now, can you tell me if value of KH will be more, solubility will be more or less? Solubility means mole fraction of gas. I think you got it. You got it? That higher KH will have lesser solubility. That means helium gas will be less soluble in water, in liquid solvent than hydrogen. And hydrogen will be more soluble than nitrogen. Okay. Acha. Then value of N2, value of KH of N2 at 2 temperatures is given, which is showing that when temperature is increased, value of KH of N2 also increases. What that signifies? That means solubility decreases with increase in temperature. Okay. We commonly observe when cold drink is not properly chilled and we open the bottle of cold drink, fizz comes out. And if it is properly chilled, no fizz comes out. Again, temperature, if temperature is higher, solubility is lesser. From the value of KH, you can get it. Values of KH for some other substances are also given, other gases are also given. You can see CO2 gas. CO2 gas has this much value of KH. Okay. So the higher is KH, the lesser is solubility. But if in some multiple choice question or in some numerical, you are given the value of 1 by KH, then everything will become topsy-turvy because 1 by KH is reciprocal of KH. So if value of KH is more, 1 by KH will be less. That you can analyze when you will solve multiple choice questions and numericals. So this was about the effect of pressure. Now effect of temperature. In temperature, again, Lee-Chatelier's principle plays its role. When gas goes into liquid to form a solution, what do you think? What will be the value of delta H? What will be the enthalpy change? Will it be positive or negative? Will the process be exothermic or endothermic? Can you guess? Yes, you can guess. You see here, when temperature is increased, when gas and liquid mix together, gas molecules come close, forces of attraction come into play. Delta H will be negative. It means solubility is exothermic process. On the other hand, in vice versa direction, delta H will be positive of same magnitude. Okay. So the opposite is true of gases. Higher temperature drives gases out of solution. If we increase temperature, reaction with this, sorry, not reaction, this process, this physical process of dissolution will go in reverse direction. And if temperature is decreased, it will go in forward. That is why we chill cold drink bottles to maintain its fizz. Okay. So carbonated soft drinks are more bubbly if stored in the refrigerator. Warm lakes have less O2 dissolved in them than cool lakes. Okay. So when temperature rises due to global warming, the temperature of lakes, rivers also rises, and it decreases solubility of dissolved oxygen, which becomes dangerous for aquatic animals. They start dying. Okay. In this graph, you can see the curves of solubilities against temperature for some gases. You can analyze this graph and compare solubilities of these. So this was about the Henry's law. Henry's law, relation between pressure and solubility of gas. Now, what are the applications of before applications, let us study limitations. Henry's law fails sometimes. Henry's law does not hold good if pressure is very low. Then if temperature is not very low. And third, if gas is highly soluble. And fourth, the gas neither react chemically with solvent or its molecules associate or dissociate in solvent. Okay. So Henry's law is valid. Henry's law is applicable under these situations, under these conditions. Pressure should be low, temperature should not be too low, gas should not be highly soluble, and gas neither react chemically with solvent or its molecular associates or dissociate in solvent. So these are the four conditions which are necessary for a gas and liquid solution to observe, to follow Henry's law. Now, applications of Henry's law. First application of production of carbonated beverages. You know, the cold drinks are kept under high pressure to maintain their bubbling nature, which gives us taste. Then second application is scuba diving. What are scuba divers? Deep sea divers. Deep sea divers are called scuba divers. These divers are given oxygen cylinders. You must have seen in some movies the people who go down the ocean for some technical purposes, for some extra polarization purposes, they have a kind of cylinder at their back in which we give them oxygen for respiration. Normal oxygen, normal air, which is used for our breathing, contains about approximately 80% of nitrogen and 20% about oxygen. But if we fill same gas in cylinder of a scuba diver, what will happen? Scuba diver is going under water. He's under high pressure. His body is under high pressure. At this high pressure, solubility of nitrogen and of course oxygen also increases very much. And when that scuba diver gradually comes out at the surface, nitrogen gas, now you can compare the KH values of oxygen, nitrogen, and third gas, helium. From there, you will get to know that when the scuba diver comes at the surface, nitrogen gas comes out of his blood because its solubility will decrease. And nitrogen gas comes out from his blood in the form of bubbles. It blocks his blood capillaries and gives a pain. That pain is very severe and the person may even die due to that pain. And this situation is called bending. In technical terms, this situation of nitrogen gas bubbles coming out of blood of a scuba diver when he comes over the surface is called bending. B-E-N-D-I-N-G, bend. To avoid bending, that scuba diver does not have pain, he does not have adverse effect on his body, we mix helium gas into his air. Air normally contains nitrogen and oxygen. We put 11.7% helium, okay, and 56.2% nitrogen, which is normally 80%. And the remaining, that is about 32.1% oxygen. This is the composition of gas cylinder of a scuba diver. Now, when he comes out at the surface, helium is 11.7%. It will not cause bending. Why it will not cause bending? You can have these values. See, helium, the value of KH for helium is very high. It is very less soluble, and value of N2 at same temperature is almost half. You see, it is more soluble, and that of oxygen at same temperature is half of that also. So oxygen most soluble, N2 lesser than oxygen, and helium the least. That is why we mix helium gas into the air of scuba dive, okay, to avoid bending. That situation, that painful experience is called bending. Okay. Now, third application of Henry's law at high altitudes. People living at high altitudes have a medical unfitness problem, which is called anoxia. The people who live at high altitudes, like high places, Badrinath, Kedarnath, Hemkund Sahib, like these places. Okay, those people are living at low pressure. You know, as we go up, atmospheric pressure goes on decreasing. So during their respiration process, oxygen dissolution into their blood is lesser. So their body cells, their brain is receiving less oxygen. And due to this, they feel lethargic, they feel memory loss sometimes, their judgments are hazy, they cannot take clear decisions sometimes, mental retardedness type of situation, and that is called anoxia. Okay, that is also based upon this Henry's law. Then, very important function of lungs. Lungs function on this basis when we inhale, breathe, when we take air in, the pressure increases, oxygen. Now, air which we take inside contain 80% nitrogen, 20% oxygen. But KH value of N2 is more than that of O2. O2 is more soluble. That's why. And when we exhale, again, O2 comes out. Okay. So these are some more applications may also be there in different books. You can now study more and share your experience. So after studying these things, now here is a homework for you. Before giving you homework, let us take an example of a numerical problem. So the situation is that if N2 gas is bubbled through water at 293 Kelvin, how many millimoles of N2 gas would dissolve in 1 liter of water? Assume that N2 exerts a partial pressure of 0.987 bar, given that Henry's law constant for N2 at 293 Kelvin is 76.48 kilobar. Okay, so this is a numerical situation. What is given in this numerical? Temperature is given. It has no role to play, but it is given because temperature remaining constant, only then Henry's law is applicable. How many millimoles of N2 will dissolve in 1 liter of water? And you have to assume that N2 exerts a pressure of this much, and Henry's law constant is also given. Now, if we solve this numerical, first of all, we have to understand that solubility of a gas is related to the mole fraction in aqueous solution. Okay, P is equal to Kh into X, Henry's law formula. The mole fraction of gas in solution is calculated by applying Henry's law. Thus, P is equal to Kh into X is equal to P over Kh. So mole fraction of nitrogen is partial pressure of nitrogen upon Henry's law constant. Both are given. So we have got this. Okay. So this is the mole fraction of nitrogen. Now, as 1 liter of water contain 55.45 mole of it, if we have 1 liter water, 1 liter water means 1000 gram water, because density of water is 1. Okay, if water is pure, density of water is 1. 1 liter water is 1000 milliliter. 1000 ml volume into density 1 is equal to 1000 gram. So 1 liter water is 1000 gram. And what is the molarity of 1 liter water, number of moles? Number of moles is equal to given mass upon molecular mass into volume. Okay. Now, given mass of water is 1000 gram and molar mass of water is 18. If we solve it, we get 55.5. So molarity of water is 55.5. Got it? Now, so if 1 liter of water containing 55.5 mole of it, therefore, if n, small n represents number of moles of N2 in solution, okay, now we can calculate mole fraction of nitrogen. X of nitrogen is equal to number of moles of nitrogen upon the sum of number of mole of nitrogen plus and water. Okay, the formula of mole fraction is mole fraction of a component like nitrogen is number of moles of that component upon the sum of number of moles of all the components, both components. So X of nitrogen is equal to N mole upon N mole plus 55.5. And we have assumed as number of moles of nitrogen, because we are not given number of moles of nitrogen. We have calculated mole fraction of nitrogen. We know value of X and we know 55.5. We don't know N. Okay. So from denominator, we can neglect this n because n will be very, very lesser than 55.5. So we have neglected it from denominator, and n upon 55.5, by putting these values, we calculate it and it comes out around 0.716 millimole. Okay, try to grasp it, understand it. And after solving this example, now try these problems, apply your brain, and these practice problems are for you to solve. First problem, 2, 3, 4, 5, 6, and 7. So 7 problems are there. You can solve this. If still you get some query, we can discuss in our Zoom meeting. Okay. So up till now, this was the solubility of solid, liquid, and gas solute in liquid solvent. This portion was in our syllabus. Now, in next lecture, lecture number 5, we will study about next property of solutions, that is vapor pressure. Now, goodbye. Thank you.